Hello, my digital artisans. Welcome back to Conquering the JavaScript Interview. As we delve into the binary underpinnings of programming, today we're going to be unraveling the mystery of the final bitwise operator, the NOT operator. It's not just about zeros and ones, it's about unlocking a new dimension of coding efficiency and sophistication. And we're going to kick off this episode with an intriguing task of finding a numbers bitwise complement. But first, check the description down below for a link to Covalence's community membership. It's not just a treasure trove of over 300 hours of coding wisdom, content, lectures, walkthroughs, full stack programs and labs, and my in-depth React course, all for a reasonably priced $25 a month. It's your key to a realm where learning evolves with you. With every update or new course added to your arsenal at no extra cost, access to our Discord community where you can have myself, other students, alumni, staff here at Covalence help you along your coding journey in a supportive and positive manner. So dive into continuous coding and learning in your journey and shape your future with Covalence.io. So get ready to see how a simple tilde can flip your programming perspective. Let's code our way to the essence of binary brilliance. So today's algorithm is called find the bitwise complement or find the bitwise complement number. We're going to be implementing a function that finds the bitwise complement of a number. It is formed by simply inverting all bits in the binary representation of a number. That's all it does. Now, the bit code is a little bit more, it's obviously faster and more performative than the non-bitwise way of doing it. But I will say the non-bitwise way of doing it this time is actually fairly simple and straightforward. I mean, you would take a number, convert it to binary, take those binary zeros and ones, simply flip them. If it's a 0, it goes to a 1, and if it's a 1, it goes to a 0. Join them back together, output it as an integer, and you're done. So logically, that's actually very simple in code, but again, it's less performative than the actual bitwise operator version of it, but I'll show you all how to do both as I've been doing as of lately. So for some examples, this won't make sense until I break these down for you in comments like I've been doing, and my handy dandy diagram, find complement of 5 should output of 2, because 5 is 101, which means its complement would be 0, 1, 0, which is 2 in our decimal format, or our integer outputted format. So yeah, that's all it needs to do. So understanding what these look like in binary is what outputs them, it tells you what their output is going to be. So in this case, our 1, flip that to a 0. The binary output of 0 is just, 0 as an integer or decimal format, right? And then for 8, we now know is 1,000. I've been telling my wife on our walks these algorithms that I'm doing in these videos. So it's a really fun way for me to kind of like, not test my knowledge, but my wife is not a programmer, but she can figure these things out fairly well if I give her solid analogies and examples and have her and watching her think through it and see if she can figure it out is generally a pretty good litmus test for also showing beginner programmers here on this playlist how to do this. So kudos to her for always being my sounding board and a receptive individual to these crazy lunatic algorithms and the ways I solve them, the sorting stuff. All these things have been a blast attempting to explain to her and watching her figure it out. So hopefully you can also thank her as like the shadow behind me that's been helping me make these videos in a way as well. So yeah, anyway, we take this and we flip it 0, 1, 1, 1, 1, which is 7, because the leading 0 doesn't actually do anything for a binary number. So there you go. Yeah, that's what all you need to do. But again, implementing it in code is a little bit more complex than you would think in terms of bitwise operators. So in the interest of actually getting to coding fairly quickly and then actually describing what happens and showing the implementations, big O and all that kind of fun stuff, let's get coding here and we'll talk about what's going on afterwards. Now, as always, you can grab the CodePen, which will have all the completed code in it. You can just delete all that stuff and follow along with me. I do advise that you always write along with me, even if you have no idea what's going on, because that's how you begin to form the muscle memory, actually linking neurons in your brain, generating those links in your brain, so to speak, that will remember what this stuff is, right? So rather than just copying and pasting it and trying to stare at it and understand it, right along with me, even if there's 0% understanding initially, I promise it'll get there as long as you put in the work. So first thing we need to do is we need to calculate. We know that the bitwise operators will deal with the underlying binary, but something we need to do, like we learned in the last video, which I'll give you a TLDR, but we need to generate a mask. Because remember, if we're going to be doing some bitwise operations and I want to take this and flip it, we learned in the previous video, which you can find again in the description down below as a link to this playlist. Just go to the previous video in this playlist where I go over in depth what masks are for. They were like stencils for a picture or painting. In this case, I need to make a stencil that is about this long. That way I can flip certain bits in that stencil. So if we need to generate a mask that is this many bits long, we need to know how many significant bits are in our input number. So to do that, this is a clever math trick I can show y'all using, well, the math object here in JavaScript. So we can say const significant bits equals, we're going to do a math log2 of our input number. This will tell us, it computes the logarithm base 2, which again, we are in a base 2 system for binary of number, which will give the position of the highest set bit in number. So again, if our input number was 5, then our outputted value is like 2 point something, right? I can't remember what it was off the top of my head. You think I would have looked this up beforehand and memorized it? Yeah, but either way, we know the binary version of 5 is 101, and because these significant bits start counting from 0, we get 0, 1, 2. So the most significant bit is going to be in position 2 of 101 right there. But we know in terms of counting bits, we need to actually count them starting from 1, not from 0. So all we have to do is add 1 to this number. So if log 2 of 5 got us like 2.32 or something like that, we add 1 to it, we get 3.32, and you guessed it, all we need to do is floor this number before we add 1 to it. Good old math.floor coming in again. And this right here is a nice trick to know, again, a nice math trick to know about, hey, if you need to calculate how many bits a number has, you do math log 2 of that number, floor that down, and add 1 to it. So that's our trick right there. It's almost like the same thing you learn with arrays, where you do the array length minus 1 for the last index position. It's a similar kind of concept. So this is how you calculate significant bits. My cat Percy is messing on my desk just off camera here. He knows what he's doing. He's too clever for his own good. He hears me talking and he comes in here because he's like, oh, I'm going to get attention whenever I jump on the desk and Luke is talking. Percy. Okay. So this is a, like I said, clever trick just to know how to calculate significant bits. Now that we have that, we can actually generate our mask. So I can say const mask equals, and what we learned about, remember the shift operators, is that order of operations, unlike a lot of the other operators, was important. Meaning, we need to actually care about order of operations here. So what we're going to say is, I need to take and generate a mask. We're going to start with just the value 1, integer 1, and we're going to left shift that 1 however many significant bits we need. This will generate the mask that we need to match this significant bit length, right? That's the whole point of this. So we'll take that 1, shift it over, according to this, 3 bits that the input was 5, right? So the next thing we have to do is we need to flip this, because remember, the point of this stencil is to help us invert our binary, our bits. The whole point is to invert bits here. So we need to make a stencil that will get them to invert when it comes time to actually return a value. So we've generated a stencil that is like the correct length and height, for example, and now we actually need to make sure the stencil, that when we stencil it in, will correctly flip the bits to their correct value. So again, this would be 0, 1, 1, 1, 1, right? So we need to generate a mask that will not only do the correct length of the painting, but when it's time to color it in, it needs to color in correctly. And that's what we're going to do here with this little trick. We're simply going to take and subtract 1. So like I said, it creates a bit mask with all the bits set to 1 in the positions that are significant for our number input, right? So this will make more sense when I show you what it actually outputs here. But just know this, just think of subtracting 1 will flip a value from 0 to a 1 and leaves all the lower bits as 1s. It results in a mask where all the significant bits are set to 1. So for example, Yeah, no. We'll do the example here in a minute. But yeah, that's all it's going to do. It's our trick to flip all the bits on our stencil. So like I said, if the left shift made the stencil the correct length, this flips the bits, so when it's time to color in the stencil on our painting, it will be the correct values. Now that I have the mask, we're going to do a clever little trick here. All I need to do is say return media list. Now, we're going to do not, there it is, not our number and mask, and wouldn't you know it, this is how you find the complement value. So this would take an input of 8 and get us a value of, or a binary, the binary value of 8 is 1000. There we go. And when we not that number and apply our lovely little mask with some trickery to it, and we return it, we get 0, 1, 1, 1, which will be our value of 7. Or if we go back to the simple version of 5, our input is 101, applied not and mask, the and operator of mask, the and bitwise operator. We get 0, 1, 0, which is 2. So let's just see if this works really quickly here, and then I'll explain how, and then we're gonna break it down and explain how it works in a bit more in depth. But there you go. That's all there is to it. Again, with this bitwise stuff, it's always like deceptively simple. Now, our newest operator here is the tilde, or the not operator. If you have questions about left shift and, I'll try and remember to keep the images, the imgur links to this in the description down below. If not, you can look in the previous 2 or 3 videos in this playlist, and you will find a video that covers that operator specifically and has a picture to its imgur diagram. But in this case, let's talk about, oh, Luke, you embarrassment. You forgot to change the title. Well, we're leaving this one in live. I'm not going to edit this video for changing the title of this right here. I will go change it in my draw.io diagram, export it correctly, and have it upload. So the imgur link will have the correct title. Embarrassing, I know, but surprise, surprise, I'm a programmer. I'm not going to remake this whole thing from scratch every time for design's sake. I'm going to keep it consistent. I forgot to change one bit. Shun, no, Luke. Okay, but the definition, analogy, example, and the diagram are correct, however. So, bitwise not, the tilde, not the title of whatever you just saw, ignore that, takes a binary digit and simply inverts it. It gives back 1 if the bit is 0, and it gives back 0 if the original bit is 1. Simple and straightforward. I think the analogy is actually overkill, but nevertheless, analogies are always good. Imagine our bitwise not as simply a mirror at a costume party. If Bit, who is our guest, shows up without a costume, his bit is 0, the mirror will magically give him a costume, saying, haha, your result is now 1, you have a costume, and the laugh is required. If Bit shows up with a costume, then the mirror's like, I'm gonna have a play a trick, I'm a prank, your bit is now 0. So it actually, the mirror will magically then take away somebody that shows up with the costume. It inverts the whole party. So people that were prepared don't get 1, and people that weren't prepared do get 1. Right? So it always flips the appearance. So in terms of examples, not 0 gets us a 1. Not 1 gets us a 0, and that's as simple as it needs to be. Just invert whatever it is you're operating on, and you're good to go. The diagram typically looks like this in terms of logical gates. It is a triangle with a circle at the end. Whatever you want to call that. This is your invert or not gate. The input is whatever the opposite of the output. The output is whatever the opposite of the input is, and typically that is displayed with a line over the input value right there. So if we put A into a not gate, we get opposite of A, and that's typically how it's displayed there in case you ever come across that. So that is our lovely little diagram for this one here, right? So that's what we're looking at. So remember that this is as simple as it needs to be, and I'll make sure the correctly titled imgur link in the description down below has the proper diagram. Back to our code, and let's actually explain how this works down, and we'll re-explain a TLDR of bitwise operators, mass, and all the fun stuff afterwards. So we're looking at this, and let's actually think our way through it. So this hopefully does make sense in the sense that this is just a clever trick you should know. I didn't know this before kind of diving further into this video and this particular algorithm to utilize a not operator in my little bitwise basics series here. I wouldn't expect you to know this. But it's one of those things where once you've learned it and kind of memorized it, you'll have it in your back pocket forever to calculate significant bits. You can look in the actual math behind it, but that's kind of out of the scope of my video here, even though we're doing binary math. But yeah, calculate logarithm base 2 of a number, giving us our highest significant bit. Because that counts from 0, we add 1 to it, make sure that's a whole number, and we're good to go. That's all we're going to worry about there. The mask is a little bit more complex. Remember, we shift all by this many significant bits on over. That generates the mask of the correct length we're looking for. We subtract 1, which will flip all the bits to prepare for our operation down the line. The not of a number is actually a little bit more complex than it looks like, because you're like, well, wouldn't the not operator just give us already what we want? Technically, but we need to end it with a mask to make sure it outputs the correct number to complement that we get here. So, just like we've done in the past, let's actually try and break down how this works so we can understand it. So, if we have an input of 5, we get a binary of 101 for that. That's what our representation of 5 is going to be. So, our calculation of significant bits will say, hey, the math log 2 of our input number is like 2.32, something like that. Math floor gets down to 2. So let's just say this code right here, about 2.32 or something like that. Sorry, the comments will correct me if I'm super wrong about this. That's what I think it would. I mean, I can just put it into Google. What am I sitting here and trying to guess what it is? Or I can always just console log it, right? I mean, what am I doing here? I just read. I'm sitting here and overthinking what I'm doing here. Hey! I'm a genius, aka I did it like an hour ago before this video, and then I remembered it. Okay, so and then floor down. It floors down to 2. Add 1, and we get 3 significant bits. So that's how we calculate 3 significant bits for our input number. That means if we have 3 significant bits and we need to generate a mask, 1 left shift 3 gets us a starting position of 1, and then that will just shift over 1, 2, 3 bits. That is what the left shift will generate for us. Then, here's the clever trick. Again, this generated the correct stencil for us, but now we need to make sure that stencil has the appropriate, pieces carved out so we can fill it in and it will color the painting correctly with this stencil we're making. Again, that's the purpose of a mask. So, what we're looking at here is now subtract 1. So we're going to say subtract 1 is a clever trick to simply do the following. 0, 1, 1, 1. It'll subtract 1 and it will basically flip all those bits on over. And that's all it's going to do, because this is the binary representation of 8. If we're subtracting 1 from 8, we get 7, which is what this is right here. So this is our generated mask, right? 0, 1, 1, 1 is our generated mask. So next, we have to worry about the return statement, which is the anding and the notting of the number. And this is going to be important here. So we're going to say not number, which is our input of 5, which is binary 101, right? Our not number, which is 101, or rather 5. We'll do not of 5, 101 in binary, right? Just to keep ourselves remembering what this stuff is. This is where it does get a little bit more complex. So in most programming languages, to my knowledge, numbers are actually stored in 32-bit storage. This is where you also see 32 and 64-bit storage, by the way, if you're wondering where those numbers come from in your operating systems, right? Especially when you're downloading stuff these days, like, hey, you want the 32 or 64-bit operating system version. But anyway, you're going to think of programming will store even whole number integers as 32 individual bits behind the scenes and simply convert it for you so you don't have to worry about that. But what's actually happening behind the scenes is you're going to imagine that every single number is stored and represented as a series of 32 individual light switches, each representing a singular bit. In a computer, numbers are stored using this system of switches. So every time a number is stored, 32 light switches are created and set. The NOT operator will flip all switches from 0 to 1 and 1s to 0s. So the actual NOT representation of 5 is not just 0, 1, 0 in binary. It's actually going to be a lot more. So if we are thinking, okay, well, if it's actually storing 32 bits, right? I don't know if that's 32 or not. I'm just saying, if it's actually storing all those light switches, My cat just jumped on top of the computer. Percy, get down. Oh, yeah. Well, just come say hello to the camera instead of being annoying off of it. He actually meowed. He's so mad I got him. Buddy, you don't. He's being fussy. Okay. So, if it's storing all those switches, then technically, if it would flip all these, it would go to a bunch of ones and then the 0, 1, because it would flip all of them. And that's exactly what it'd be doing here. So, that flip, that not flip, is actually flipping all those zeros switches to 1 switches. So we are going to know that, again, because of how numbers are stored in most programming languages and computers are actually 32 bits, what are called signed integers, we are going to know in the back of our minds that in actuality, there is a whole host of ones that are getting flipped, or zeros that are getting flipped to ones, essentially being the negative version of a number, which is what's happening here, okay? So it's a full row of ones. If you use a bitwise NOT on a positive number, you end up with a full row of those on switches, which are a bunch of ones to the left of it, which makes the number negative in the computer's eyes, which is what actually is happening there. So in actuality, we're going to think of it, and typically you'll see it represented as like ... saying all the trailing 1, 1, 1, 1, 1, 1, ones like that. You can think of that as like all the trailing ones that are actually on this on this integer right here. And then we get 0, 1, 0 there at the end. That's our actual like flip parts right there that we're staring at. And that's what we're looking at, okay? So that is our not number. So now that we have not number, which we're going to represent by that and the actual bits that we flipped right there, I'm going to space them out, right? So that's our not 5. That's what we're looking at. Then we have our, you guessed it, our mask, which was, I'm going to match it over here. 0, 1, 1, which we know is our mask. Okay, I'm going to try and align these things up here. Yeah. Okay, and as you know, when comparing binary numbers, then you would just, yeah, so, okay, we have our number, we have our mask. So now all we need to do is do the AND operation on this one, and then what we know about AND is we get, if it's a 1 and a 0, we get 0. I forgot to add the comment line here. Oops. We get the comment line here, and we get the, if it's a 1 and a 0, we get a 0, as a matter of fact, just so we can refresh everyone's memory, as I'm also going to try and remember to include this up here. Hold on. That's because I'm so zoomed in. Bring up that AND diagram, please. There we go. Remember, if it's 0 and 0, we get 0. 0 and 1 gets us 0. Remember, this is the strict security guard. So both people got to get a VIP pass in order to pass. So if anyone is missing a pass, we get a 0 in this particular case. So that's what we're looking at here. So yeah, these two got a pass. One person's missing a pass. And that's what we wind up with right here. Like if we do the not of our number and apply our mask to it with the AND operator, we get 0, 1, 0, which is our binary output of 2, which is just 1, 0, which is 2, because we have 0, 1, 2. So there you go. There's our output of 2 and how we got it using our not and our mask. So TLDR, remember, Bitwise Operators. As I'm trying to teach y'all what this stuff is. They're functions that operate on binary integers at the level of individual bits. We got several types that we've done in this video series. And, or, not, XOR, left shift, right shift. Each one takes a binary piece of data and morphs it in a unique way following rules of binary arithmetic. This is how our computers just work under the hood. Putting it in plain English, if you had to explain this in an interview, remember Christmas tree light analogy, where each bulb is a bit, light switches also work. Bitwise operators are like switches that you use to control which lights are on and off. You can combine switches, light up more with a single switch, flip all switches with NOT, or even make sure unique lights are on, like with the XOR operator we learned in one of my first videos. The shift operators are like moving the strand to the left or to the right to create unique patterns. It's all about manipulating lights on Christmas tree lights to create that dazzling display you want. Now, while I did a more in-depth explanation of masks in a previous video, as a quick reminder, the mask is right there. A bit mask, or a mask, is a binary number used to selectively modify, observe, or manipulate specific bits within another binary number. Aha! So because I'm trying to find a number's complement, I'm going to use a mask to get there. I've been calling it like a stencil. We're going to be using a stencil while painting. A stencil is going to cover certain areas of the canvas, allowing paint to apply only through its cut out shapes. So the left shift significant bits builds the stencil be the correct size. The -1 will then make sure our cutouts are the parts that correctly paint in order to cover certain bits of a number, allowing operations only to affect our exposed or our selected bits. And the -1 part does that for us. Just as a stencil can have various shapes to control where the paint goes, a bit mask can have various patterns to control which bits are affected in a number. So again, in our case, it's just like making sure that only significant bits of a number are inverted, and we ignore all those leading ones in the not number because our mask has the significant bits for our number, right? And they are left unchanged. This ensures the complement operation is accurately performed with the relevant binary length of a number. Our mask is what ensures that. Because without the mask, we would have to worry about all those preceding ones in our 32-bit signed integer, our negative version of not 5. So that is all thankfully ignored because of our good friend the mask here. So, continuing on, let's go ahead and see if this correctly works. Oh, because I forgot to save. There we go. Yeah, it's 2 is what we're looking at right there. So, let's see if this works for find complement of 1. This will be a bit more straightforward. If I complement find of 1, we get 0, which is the correct answer. So, in our case here, we get an input of 1. Binary is, well, also 1. Our math log 2 floored add 1 gets us a significant bit count of also 1 because that's how long it is. I think this would generate probably near 0. Let's test it. Let's just test it really quick. So let's go ahead and do a console log of 1. Rounds down and math floors out to, or just straight up 0. We add 1, we get 1. So that's how many significant bits we got. Sig bits. We're going to call it sig bits instead of significant bits. I'm too lazy to write it at this point. So if that's how many significant bits we have, our mask 1 shift 1 gets us about 1 0, which is binary 2. Not of 1, which is 1 in binary, pretty much gets us, as y'all know, the negative version of it with all those flip bits in front of it. And basically, instead of 1, we flip it to 0, and that's all we get there. So then our operation of that right there, our mask of, it'd be 1 0 is our mask. And then we AND it all together. 0 and 0 still gets us 0, and that's it. So this is our output for our significant bits with our mask work doing its job here, right? So is 0 our output? It sure is. We can see there. 2 was the one from 5, and then find complement of 1 is indeed a binary output of 0. So the final one is find complement 8 as our example, and let's work our way through it again to try and make sure we get understanding of what's going on here. We should expect, let's see, input 8, binary 1000. That significant bits, it'll calculate as 4, right? Yeah, I'll calculate significant bits of 4. So 4 sig bits will be the calculation. Our mask in that case will be 1 shift 4. Oh, I forgot to, oh goodness. How did I wind up with the right answer? Because I forgot to flip. That's odd. Hold on, because we forgot to do the flip, right? Because we had to still subtract 1, which technically get us 0 and 1 as our mask right there, right? Would be the actual mask. Okay, that's why. That's why it wouldn't matter, because it's still and an and of 1 and 0 is 1. So even though my input was wrong, I got lucky in that my and operator has a property saying it doesn't care which order the arguments are in. As long as one is a 0, they both end up 0. So whoopsie. Sorry about that, guys and gals. I was looking at it and I was like, something feels wrong about that. I forgot something from my tests earlier. And that's what I forgot. The subtraction of 1 to flip those bits in our stencil here. But thankfully, because this is commutative, I got lucky. And hey, again, even though I practice these, I write the scripts for these videos, I'm still prone to making mistakes because I'm human. It's about if I just follow your gut. If something doesn't feel or look right, then investigate that and ask why and figure out why. And you learn something from it. And I like to leave my mistakes in like this unless they cause like a long amount of dead air. But let's go back down to here. We have 4 significant bits. We do a 1 shift 4. So we're going to do 1, 1, 2, 3, 4 as our mask. That is our mask. With the left shift, subtract 1 in our mask and we get 0. 1, 2, 3, 4 as our mask. There's the actual generated mask we got for this one. I can't believe I forgot that in the last one. So the not of 8, we know is 1,000. So we know we're going to get 0, 1, 1, 1. But we know that the whole thing is preceded by a whole bunch of other flipped ones as well because of our 32-bit signed integer storage in JavaScript. 32 bits, not integer. 32-bit signed integer storage, my goodness. So we know it's a whole bunch of trailing ones before that because all those light switches were flipped. That is our not number. So then we're going to do our not number, right? Not 8. We're going to do our mask, which we know is 1, 1, 1, 1, and then the 0 technically at the beginning. Which doesn't matter in this case. That is our mask we're looking at. And then we're going to do our you know it and logic on these two. And we're going to get, if it's a 0 and a 1, we get 0 and we get 1. If it's a 1, if it's a 1, etc. So we are generating our number, which we know this is the binary for 7 as the output. Because if 1,000, because remember, if 1,000 is 8, we subtract 1, we get 0, and then the rest flip to 1s. That's a 7. So our output should be 7. Survey says it is indeed a 7 when we put the input number of 8. So I did say that this is actually a bit more complex than just doing this in vanilla JavaScript. And if you didn't know Bitwise Operators, right? So this is super cool to know how to do. But let's see how it implements without it. So we're going to say function find complement non-bitwise input number. What we need to do is, like before, we can take the number and convert it to a binary string by calling .toString, pass in a base of 2. That gets us a string value of our binary number. Then all I need to do is generate a new string based off of each character in our binary string. So I will say we're going to generate a complement string, who will be an empty value to start. We're going to loop through each character of the binary string. And for each character, we're going to simply concatenate into the complement string based on what the character is. If the character is the string value 0, we're going to concatenate a 1. If it's not a 0, we're going to concatenate a 0. There is our not operation going on in play, right? Just simply toggle the switches up and down based on their previous position. Then after that, all we need to do is return our number parsed back into an integer from our complement string, which is inputted as base 2, right? Or a radix, whatever this argument was. Radix, whatever it is, yeah. So that's the base number of our string. So our string is in base 2. We're going to parse it into an integer. So if I console log find complement non-bitwise of 8, please output 7. It got 7, and there it is right there. So I told y'all at the beginning of the video that the non-bitwise version is actually easier to understand and look at in terms of flipping. So again, ease of reading might be the way to go, but obviously this other one up here is going to be far more performative. That is because we have a big O. We have a big O time of, I'm pretty sure this is a big O time of, if my notes are, yeah, so it's time of 1 and it's a space of 1. Right? That is because the math, assuming that math log 2, that operation, and the bitwise operations are constant time, the number of operations here does not depend on the size of the input, but rather the fixed number of steps required to compute the complement. It is always a fixed number of these 3 steps to compute the complement. It's easy. And in terms of space, it uses a fixed amount of extra space for the variables significant bit and mask, and the space needed to store the result, and that's it. It does not require to grow. The bigger the number gets, significant bits and mask aren't going to grow to be massively larger anyway. Because remember, like, these things always are are stored as the same 32-bit length, 32-bit length, 32-bit length, 32-bit length, even though we don't see it. So that's why it is a constant space. But that means, again, on the graph, it is literally just the straight line at the bottom. That's as awesome as it can possibly get. Now, in terms of the other function, even though it's far easier to understand and read, it does have, and again, I learned about this recently, it has a time complexity of k and a space complexity of k. And you're wondering, Luke, why not use n? Because n typically in big O is for our input, which is in our case our number. The bigger this number grows, the more iterations you're gonna have to do in terms of our time complexity. But we're not iterating directly over our input. We are iterating over its binary representation. So in this case, k typically represents the number of bits in the binary representation of our input n number, right? Because it has to iterate over each bit in the string at least once. And in terms of space, same thing. Because this creates a new string, the new string will grow to however many bits our input number, typically n, generates. Hence why we use k to designate this, because we're not iterating directly over a number, we're iterating over its binary representation, which is typically done with a k in big O. And O of k can be assumed to look like n. The bigger the number grows, the more binary representation we're going to have to generate out. We're going to have to iterate over it at least once, grow the string with it, and that's why our time and space ends up being this linear line right here, represented on the traditional big O diagram. So that's it. This is our final operator in this little mini series called Bitwise Basics. We have done some crazy stuff with it. We know that this is just fundamentally how a computer operates under the hood. We know it's extraordinarily efficient, extraordinarily optimized in terms of memory usage. And it's just incredible for logical operations and algorithms when you can apply them. If you ever go into a field that does any kind of DSP or digital signal processing, you will see a lot of this for manipulation and transformation in audio, video, image processing, cryptography, probably all over the damn place, error detection and correction. We talked about in previous videos, hardware control. In embedded systems and hardware programming, Bitwise operations are used to control hardware components all the time, because the configuration of certain things on your computer are done in binary under the hood, and this is how you toggle certain switches on or off using logic, right? Graphics, also a place you're going to see it a lot. Color inversion, masking, bit level image editing. This is where it's all done right here. So yeah, I might do a few more Bitwise algorithms now that we've covered all of our operators. I might do a couple more of like the most common algorithms you'll see for bit manipulation. And after that, I want to show y'all my Quake 3 algorithm, where I told y'all was one of my favorite algos, and I completely forgot its name and its purpose in the previous video. Embarrassing. Hashtag embarrassing. But I got it right in this one. The Quake 3 fast inverse square root algorithm I'm going to cover like as a history, and we'll break it down and the bitwise logic it uses to achieve that now that you know them all. So that's how you unleash the power of bitwise complements to flip the script on standard numerical operations, right? So go ahead, please give us a thumbs up, subscribe for more enlightening content, hit that bell notification to see more videos when I pop them up, typically on Tuesdays and Thursdays, and sometimes Wednesdays, and my coworker Matt sometimes on Fridays, and my coworker Andrew sometimes in between that. We all like outputting content on here. So leave a comment and share your thoughts, experiences, or the creative ways you've applied Bitwise operations in your projects. If you're eager to dive into more digital depths, consider joining our vibrant community and our community membership. But remember, keep on flipping those bits, keep coding, and until next time, may your logic be flawless.